Okay, so last time we talked about, we introduced yet another graph search strategy called depth first search, DFS. Okay, so just to remind you, intuitively, it also explore, starting from a source node, it starts to explore other nodes one by one, but then the order that is going to explore other nodes is based on the, it explore those newest discovered nodes, namely those in the pending list that's just the most recent discovered first. Okay, so this is opposite to the choice made by breadth first search. Okay, and as a result, starting from the source node, we keep trying to discover newer nodes, more and more newer nodes before finishing one node. So that's why this is depth first search. Okay, and so here is the overview of the entire algorithm. And to explore the newest discovered pending nodes first, okay, intuitively, we want a data structure to support the so-called first in, last out, okay, which is a stack data structure. And in implementation, we actually use the recursive algorithm to implement that. Okay, so this is the algorithm, and as we said last time, the time complexity of this algorithm is the same as the BFS, which is proportional to the total size of the graph, number of edges plus number of nodes. Okay, so today we're going to talk a bit more about this algorithm and also property of this one. Okay, remember, property of BFS is that it actually visits all the nodes in increasing order, shortest path distance to the source. Okay, DFS doesn't have that property, but it has its own property. Okay, but first, let me also remark that similar to the breadth first search, BFS, for every node, we again can remember its so-called predecessor along the shortest path reaching this, along a path reaching this one. Okay, so the predecessor of a node is simply during the exploration, who discovered node V? When was V first discovered? So basically, if we first discovered V when we're exploring the neighbors of U, then U is the predecessor of V. Okay. And we can remember this predecessor information in the DFS algorithm as well, okay? And the collection of such edges will also form a tree called a DFS tree, okay? But this tree is different from BFS tree, where in particular, BFS tree in the breadth first search, the predecessor will remember basically it's actually give you the shortest path information. Okay, this is not the case in DFS tree. Okay, so let me just mark it here. DFS tree does not contain shortest path information. Okay, so this is different from BFS that we talked last time. Okay, all right. Now there's something else that we can actually record for the nodes when during a DFS exploration. Okay, in particular, note that during the DFS, let's say that we start with the source node S, and then immediately we discover one is neighbor, say A. Before looking at exploring any other neighbor of S, we first immediately start to explore A, and then says who can we discover? And in this case, we discover E, and then before we finishing looking at other neighbors of A, we immediately start to explore E, and so on. Okay, so now note that A will only finish exploring A after we finish exploring many other nodes. And in this particular case, we then have to go all the way backtrack to A. Okay, now the first time we discover V, we change its status from undiscovered to pending. Okay, and then to change from pending to finally finishing exploring A, namely we're going to change the status to be visited. This is going to be a while, and in between we will, visit many other nodes and update their status from to pending or to visit and so on. Okay, so now in particular, record that a node the status can change either from undiscovered to pending or from pending to visited. Okay, so what we can do now is that we're going to keep kind of an integer running clock during this DFS procedure, okay? And for every node, we're going to record the start time, namely the first time that we discovered this node, which is when the status changed from undiscovered to pending, okay? Then we also record a finish time for every node. This is time that we finally finish exploring all the nodes, all the neighbors, and their whoever they can reach, and then come back. Okay, so that is one. We change the status from pending to visited. So we're done with exploring this node. Okay, so in the recursive algorithm, that's when we finish this recursive call and then return to the previous function that's calling this recursive call. Okay, so we're going to mark for every node, give them record a start time and a finish time. Okay, and this clock incremented by 1 whenever some node has a status change. Okay, and if we do this, we can record this together with our previous information. So here is a full DFS algorithm, including the marking of start and finish time, as well as the predecessor information. Okay, so this is a modification of the previous one. So the changes are now, whenever we first discover a new node, okay, so that new, if we explore a node U and then look at its neighbor V, and if this V was undiscovered, that means that this is the first time we discover a node V. Okay, in that case, we add that we also record the predecessor of V to be U. Okay, and the other the change that we have is that we change the start time. Oops, I think yeah. So when we visit the so this is a one change that we have. The other one is that we'll also record the start and finishing time. So when we meet a new node, then we start to call this DFS times. We recursively start to explore this node, and that's when we record the start time of exploring this node. Okay, and then after we finish exploring all the neighbors of this node, that's when we update the status of this node to be visited, and that's also when we change the finishing time. Okay, we record the finishing time of this node. Okay, and every time we have a status change, we increment the clock by 1. Okay, so this is what we have. Okay, so as we see that this is when we have a status change, that's why we have a clock would increment by 1. Same here. Now we're going to change a node from pending to visited. Then at that point, we increment the clock by another 1. So every time there's a status change, the time this clock will increment by 1. Okay, so this algorithm clearly has the same time complexity as the previous DFS algorithm, because whatever we're adding only take a constant time per node or per edge. Okay, so the total time of this modified full DFS algorithm still takes linear to the size of the graph, which is number of nodes plus the number of edges. Okay, so this time complexity remains the same. All right. Okay, so why do we talk about this starting time and finishing time? Okay, it turned out that for DFS, there are certain properties associated with this starting and finishing time, which we're going to look at. But first, let's go through one example to look at the start and finishing time. So this is the same example we went through before. So let's say that we start our DFS first at source node S. Okay, what does that mean? That means that the start time, so I'm going to record for every node a start time, I use S to represent, and a finishing time, I use T to represent. Okay, so when we start visiting S, we change the status to be pending. At this point, we change the start time to be 1. Okay, then we explore S and then find discovered A. And then DFS immediately start to explore A. Okay, that means that now we start to explore A and change the state of A to be pending. So the clock increment by 1. Okay, finishing time, we don't know yet. And at A, we immediately start to explore E. okay? So the status of E changed to be pending, so the clock increment, okay? Same from E, we go to H, okay? So then at H, we change the status to be pending, so that's when the start time is 4, that increment to be 4, okay? And at H, we explore to identify the node neighbor G. So the start time for G become 5, and then G, we first remember among all neighbors, we explore them in increasing order of their labels. So first we explore F. So that means that the starting time for F is 6, okay? And so far we just keep discovering new nodes, okay? And then at F, we look at its neighbor that give us 2C, okay? So then the start time, we first discover C at the time 7, okay? Then at C, we look at its neighbor. The first neighbor we look at is E. But the E is already discovered, so we come back. There's no status change, so our clock doesn't increment, okay? Then we look at the next neighbor, go to G, okay? G is also already discovered, which means again, we do nothing, and then we come back, there's no status change, okay? So the clock doesn't change either, okay? Now after G comes back, we realize that we don't have any more neighbors of C, so we're done with C. So finally, we can mark C now to be visited. So we increment the time to be, 8, and that's when we finished exploring C, okay? Then we go back to the function that calls C, where we discovered C. So in fact, let me mark all this predecessor edges connecting a node and its predecessor with some red, okay? So this are red. So then we know that we found C through F, so we go back, okay? At F, we look at, are there other neighbors of F? No, we don't have any other neighbors, so F is done. So at this point, the finishing time, F is finished, so we increment the clock and the finishing time of F is 9, okay? Then we go back to the node who discovered F, which is the function we called F, and that one, we look at this one. So we say, okay, this one has other neighbors, and we also have neighbor, G has neighbor H, but then H is already discovered. So this one, we don't do anything. There's no status change, so clock doesn't change either. We go back, and then G also has a neighbor, which is I, okay? I is a new node, which means that now we discover a new node with time 10, okay? And this is also, we discover a new node, so predecessor for I is G, so we mark it as red, okay? Then we continue to explore I has a neighbor, which is H, okay? But H is already discovered, so we don't do anything, we come back, and I doesn't have any other neighbor. So exploration of I is done. At this point, the finish time, we discovered I at time 10, and we finish exploring at the time 11, okay? And this means that we go back to whoever discovered it, which is G, okay? Now, there are no more neighbors of G, so exploration of G is done, so we mark the finishing time to be 12, okay? Then we go back to whoever discovered G, which is H, its predecessor, okay? And then H, there's no more neighbor of H, so then H is also done. The finishing time is 13. We go back to its predecessor, okay? And E is its predecessor, and E doesn't have any other neighbor too. So we then mark that, okay, we're done with E as well. Finishing time is 14. We go back to its predecessor, which is A, okay? And then at A, we also don't have any other the neighbor to explore. So the A is also done. Its finishing time is 15. We go back to its predecessor, which is S. At S, we do have another neighbor to explore, which is C. But C is already discovered. We discovered it during the processing of A, okay, while exploring A. So then there's nothing we need to do. We come back to S, okay? Now S doesn't have any other any other neighbor anymore. So the exploration of S is finally done, and the finishing time is 16, okay? And we run the full DFS algorithm, at this point, we continue to scan the list to see who else is undiscovered. And then we realize that the B is undiscovered. And we discovered the B, so we set its starting time to increment every time the status change, you increment the clock by 1. So starting time is 7. And then the neighbor of B is A. We explore it, but A is already discovered. So there's nothing to do. We come back, and then there's no more neighbors of B. So the finishing time of B is 18. And now we finish scanning the entire list. There's no more nodes that's undiscovered. So the entire process is done. And this is what we have. Okay, the starting and the finishing time. Okay, all right. So now this is how we compute it. And it turned out that this start and the finishing time has an interesting nesting property. Okay, so in particular, let's see how I can keep some of this while go to the next page. Okay, so I'm going to just clear this. In particular, so here is one important nesting property of the depth first search. Okay, so you pick any two neighbor, say U and V, two nodes, U and V in the graph. Okay, and assume that during the DFS exploration, the start time of U is smaller than the start time of V. Okay, then it turned out that one of the two has to be true. What does this mean? Let's just draw a picture to see it. Let's say this is my time. This is axis of time. Okay, and let's say that we first discovered U here. So this is start U. Okay, and assume that we discovered the V later. Okay, what this is saying is that now the finishing time, actually let me use a different color for V. So this is time. And this is start V. Okay, so where can their finishing time be? It turned out that either the start time, the finishing, you first finish V before you then finish U. So this is a case 1. Okay, the second case is that you start to explore U and then you finish. Oops, it's the wrong color. Then you finish U. Then you start V and then you finish V. Okay, so this is case 2. Okay, so only these 2 cases are possible. Okay, so what is not possible? The following is not possible. That means, so this is not possible. So this is not possible. Let me actually use the red color to show that this is not possible. So which is that you start U and then you finish U here. But then you start V here and you finish exploring V here. So this case, the last row is not possible during the DFS traversal. Okay. In other words, if you look at this start and finishing as an interval, right? So here, this intervals are nested. Either the red interval the start and the finishing time, the lifetime of U. You can think of start and finish as the lifetime of U. So either the lifetime of U includes the lifetime of V. Okay, so they have the nested relation, or the lifetime of U is completely disjoint with the lifetime of V. Okay, so you start with one, you finish the exploring U before you start V and finishing V. Okay, so it's not possible. The last case is not possible, which is that the lifetime of U and V intersect, but yet they don't have the containment relation. Okay, so this is why sometimes this result is called a nesting property, because essentially what this is saying is that if you look at the start and the finishing time of each node, the time you discovered and the time you finish exploring it, okay, that time range and the time range of any other nodes, they either are completely disjoint or they have containment relation. One is nested in the other. Okay, so the last case, this one is not possible. This cannot happen. Okay, all right. We're going to see very soon how to use this property. I mean, there are different consequences of this nesting property, and then later we're going to see an application of this. Okay, how this is useful. Okay, all right. So this also implies the following. Okay, which is again, you take two nodes U and V, and assume in this case V is reachable from U. So this is U, and suppose in your graph V is reachable from U. Okay, so if that's the case, then also assume that you first visit U, okay, before you visit the V. Okay, so this is just a kind of corollary from the previous claim in the previous slide. Okay, then it must be the case that this is the only possibility you have. Okay, what does it mean? It means that if V is reachable from U and you explore U first, then in the time axis, it must be that you first see U, discover the U, and then during the exploring of U, you discover V. And then you have to finish V. Oops, finish. Before you can go back to its predecessor, okay? And so in the end, you come back and finishing U, okay? So this is the only relation that can hold if V is reachable from U and I discover U first. Okay, so this is quite natural. What this is saying is that during the DFS algorithm, if I first discover U, then remember that because DFS always start to explore its neighbors first. So then we will start to explore all its neighbor. And if V is reachable from U, at some point during this exploration, I will be able to find V. Okay, and if V was not yet already discovered, that means the start of V is later than starting time of U, then I have to first explore all the neighbors of V first, okay? And then after I finish exploring all of them, so then I come back and finish explore V. That's when I can go back to its predecessor and then backtrack. And in the end, backtrack to U. And then if U has other neighbor, I still have to finish them before I finish U. That's why the finishing time of U will be later than the finishing time of V. In other words, it'll be later than any nodes that's reachable from U. Okay, so this is a very kind of an important observation. Okay, so another way to say this is that intuitively, when we explore a node U, we basically will explore all the reachable nodes from U. Okay, and they need to be finished exploring them before we finish exploring U. Okay, so me and my descendant, actually the finishing time for me will be later than the finishing time of my descendant. Okay, all right, questions? All right, so this is just a consequence of the claim we had in the previous slide. And another result starting from using this is that the following one, which is the one that we'll use later, which is in general, if a node V is reachable from U, okay? So then the finishing time of V will always be earlier than the finishing time of U, Okay, so this is different from my statement here, because here I assume that the starting time of U. So in this case, if the starting time of U is earlier than the starting time of V, if I discover U first, then we know that the finishing time of V has to be smaller than the finishing time of U. Okay, so this claim says that it doesn't matter what's the relation between their start time. Okay, so even if the start time of U is bigger than the start time of V, then this finish time still needs to hold. Okay, and this is against the consequence of previous slides, because suppose that V is reachable from U. So this is okay, and suppose that the start time of U is bigger than the start time of V. Okay, what does this mean? This means that I first discover in my DFS exploration, okay, we first discover V. Okay, and now when I discover V, I will only explore everything that's reachable from V, essentially using this. Okay, so that would not do anything to U. Okay, so then I would have to finish this before I later kind of coming to U and then start to explore it. Okay, so if V is discovered first, okay, then basically I will not touch U till I finish exploring U. V. Okay, so essentially using the previous claim A, this basically would suggest in that case, okay, in that case we would have to have that the start time of V is smaller than is finish of V before we go to start of U and the finish of U. Okay, so this still implies that the V has to finish before U finishes. Okay, so combine this observation with this, then it doesn't matter whether who is discovered first, U or V. Okay, in either case, V has to finish first before U finish. Okay, a simple way again to remember this is that if a node V is kind of reachable from U, okay, then we definitely would have to finish exploring V, the descendant, before we can finish any of its ancestor, essentially. Okay, so this is the claim. All right. Okay,